Welcome, everyone. Ready for another deep dive. Today, we're tackling spherical trigonometry.
Sounds a bit intimidating, right?
Maybe a little. But don't worry, we've got excerpts from the Wikipedia article on spherical trigonometry to guide us.
Yeah, and it's way more interesting than it might sound at first. We're basically talking about triangles, but not the kind you'd find on a flat piece of paper.
So not the ones from high school geometry class.
Nope. These triangles live on a sphere, which makes things a whole lot more, well, spherical.
Okay, so curved surfaces instead of flat planes.
Exactly. Think about it. The sides of our triangles are now arcs of great circles. It's like geometry on a whole new level.
So if I picture slicing an orange, each segment would kind of be like a spherical triangle.
You got it. And you know those spherical triangles, there's like the building blocks for even cooler shapes, things called spherical polygons.
So we're talking about shapes made up of these curved triangles.
Exactly. Now imagine like a five-pointed star on a ball where all the points are right angles. That's a spherical polygon called the pentagramma mirificum.
That sounds pretty complex.
It is, in a way, but also kind of beautiful when you think about it.
Definitely. So before we get too lost in all these shapes, can we take a step back and talk about notation? How do we even represent these spherical triangles?
Good point. Always good to clarify. So we use capital letters like A, B, C for the angles, and lowercase letters A, B, C for the sides.
Makes sense. And anything else? Any assumptions we're making?
Well, to make calculations easier, we usually consider the sphere's radius to be 1 unit.
Okay, I can see how that would simplify things. Now, I've heard about these things called polar triangles. What are those all about?
Polar triangles. They're like the alter egos of our original triangles.
Yep.
Every spherical triangle has a corresponding polar triangle where the sides and angles are kind of switched around.
Switched around how?
So the angles of the original triangle become the sides of the polar triangle, and vice versa. The sides become the angles. Kind of a neat mirror image thing going on.
Interesting. So if we figure out some equation that works for a spherical triangle, could we flip it around and use it for the polar triangle too?
Exactly. Any identity that works for a triangle also has a counterpart for its polar triangle. It's a cool symmetry that pops up in spherical trigonometry.
2 for the price of 1. Okay, now I keep hearing about the cosine rule. You mentioned it's like super important in spherical trigonometry. Why is that?
Well, the cosine rule is like the key that unlocks a lot of doors in this field. It basically connects all 3 sides of a spherical triangle with one of its angles.
Can you give us the formula for that?
Sure. So the cosine of side A equals the cosine of side B times the cosine of side C plus the sine of B times the sine of C times the cosine of angle A. And we can switch that around for other sides and angles too.
Okay, so it's a bit more complex than the cosine rule for regular triangles, but I see the similarities. Now, what about the sine rule? Does that play a role here too?
It does. The sine rule in spherical trigonometry says the ratio of the sine of an angle to the sine of its opposite side is constant, no matter which angle and side you pick. And guess what? You can actually derive it from the cosine rule.
So it's like a domino effect. One rule leads to another.
Exactly. And, you know, there are actually a bunch of other identities in spherical trigonometry, too. Things like supplemental cosine rules, cotangent 4-part formulas, half-angle and half-side formulas.
Whoa, that's a lot to keep track of.
Oh, yeah, there's a whole toolkit of formulas to work with. And we've also got D'Alembert analogies and Napier's analogies, just to name a few more.
Wow, sounds like a whole new language to learn.
Yeah.
But I'm guessing not all of them are equally important for, say, our STEM audience. Which one would be the most useful, especially when dealing with right triangles?
Great question. For right triangles, Napier's rules are a lifesaver.
Napier's rules, tell me more.
So there are 10 of these rules, and they connect the different sides and angles of a right spherical triangle. The best part, you can remember them all using this cool mnemonic device called Napier's circle.
A mnemonic device. Sounds intriguing.
Right. So picture a circle that represents the right triangle. The sine of a middle part equals the product of the tangents of the adjacent parts, or the product of the cosines of the opposite parts.
Okay, but how do we figure out which part is middle, adjacent, or opposite?
Easy. Just look at the first vowel in the name. S in sine means middle, T in tangent means adjacent, and C in cosine means opposite.
That's clever. I might actually be able to solve a right spherical triangle now. But what about the non-right angled ones? How do we solve those?
Good question. Solving a spherical triangle basically means figuring out the missing sides or angles if we know some of the others.
It's like a puzzle.
Exactly. And like any good puzzle, it has different cases. Like you might know all three sides, which is the SSS case, or you might know two sides and the angle between them, the SAS case, and so on.
So different cases, different approaches.
Yep. You have to pick the right formula or method based on what you know. Like for SSS, you could use the cosine rule directly, or maybe the half-angle formulas if you want a more stable calculation.
Got it. It's all about choosing the right tool for the job. Before we move on, can we talk a bit more about spherical excess? I feel like that's a really important concept that sets spherical trigonometry apart from the flat stuff.
Absolutely. Spherical excess is key. So remember, the angles in a spherical triangle always add up to more than 180 degrees, unlike those flat triangles we're used to.
Right, because of the curvature.
Exactly. And that difference, that extra bit, is the spherical excess. Now, there's a cool theorem called Girard's theorem, and it tells us that this excess is actually equal to the area of the triangle, at least if we're talking about a sphere with radius 1.
So the bigger the triangle, the more excess it has, and the bigger its area.
You got it. It's all tied to the curvature of the sphere. It's like the triangle is trying to lie flat, but the sphere forces its angles to open up, creating that excess.
So even though it seems like a small detail, this spherical excess really changes how we think about triangles on a sphere.
For sure. And it turns out to be super important in a bunch of fields like geodesy, where people need to make precise measurements on Earth's surface.
It's amazing how this seemingly simple idea has such a big impact. So where do we go from here?
Well, in our next segment, we're going to dive deeper into some of those real-world applications and see how these spherical trigonometry concepts are used in practice.
Sounds like a plan.
It'll be fun, I promise. We'll even uncover some hidden connections between spherical trigonometry and other areas of math that you might not expect.
I'm intrigued. Looking forward to it.
Me too. Stay tuned. Welcome back to our deep dive into spherical trigonometry. So last time we laid down the basics, talked about spherical polygons, the cosine and sine rules.
Right. And those Napier's rules for right triangles, which were pretty cool.
Oh yeah, and who could forget the spherical excess? But now, let's shift gears a bit and see how all these concepts are actually used to solve real-world problems, stuff that's relevant to folks in STEM fields.
Yeah, let's get practical. So you mentioned solving spherical triangles earlier. What does that actually involve?
Okay, so solving a spherical triangle basically means figuring out the missing pieces of the puzzle, right? Let's say, some of the sides and angles.
We need to find the rest.
Exactly. It's like having a partially completed jigsaw puzzle, and we use those formulas and identities we discussed to fill in the blanks.
So it's all about using what we know to figure out what we don't.
Yeah.
I'm guessing there are different scenarios depending on what information we have to start with?
Oh, absolutely. That's where the cases come in. Remember we talked about SSS, SAS, and all those combinations?
Yeah, those were the different ways of knowing the sides and angles, right?
Exactly. Each case requires a slightly different approach, a different strategy for solving the puzzle. For example, if we have all three sides, the SSS case, we could use the cosine rule directly to get the angles.
Okay, makes sense. But are there other ways to tackle these cases?
Oh, tons. Sometimes it's helpful to split the triangle into two right-angled triangles and use Napier's rules, or we can use something called the Delambre analogies or Napier's analogies.
Whoa, lots of options.
Yes, spherical trigonometry gives us a whole toolkit to play with, and the trick is knowing which tool is best for each situation. It's like being a chef who knows when to use a whisk versus a spatula.
I like that analogy.
Yeah.
So can you give us some real-world examples of where this all comes in handy? Like, how's spherical trigonometry used in navigation?
Navigation. That's a classic example. Imagine you're a ship captain, and you need to find the shortest route between 2 points on Earth. Now, on a flat map, that shortest route would look like a straight line. But remember, Earth is a sphere.
Right, so a straight line on a flat map isn't really the shortest distance on a curved surface.
Exactly. The actual shortest path follows a great circle, which is basically a circle that cuts the sphere right in half. And spherical trigonometry lets us calculate that great circle route precisely, figure out distances and bearings for optimal navigation.
Wow, that's pretty cool. It's like those flight paths you see on those maps, right?
Yeah.
They're curved to take advantage of those great circles.
Exactly. It's all about efficiency and accuracy. And what about surveying?
Surveying, yeah. How does spherical trigonometry come into play there?
Well, surveying is all about measuring distances and areas on the Earth's surface, right? And when you're dealing with large areas, you can't ignore the curvature of the Earth.
Right, because otherwise your measurements would be off.
Exactly. So spherical trigonometry gives surveyors the tools they need to take that curvature into account and get accurate measurements.
It's like those calculations are adjusting for the Earth's shape.
Yeah.
Okay, let's talk a little bit more about spherical excess. I'm still kind of fascinated by that concept. What's the connection between spherical excess and the area of a triangle?
Okay, so remember, the angles of a spherical triangle always add up to more than 180 degrees. That's the spherical excess. And Girard's theorem, that neat little theorem we mentioned before,
Yeah, the one that links the excess to the area.
that's the one. It basically says that the spherical excess is equal to the area of the triangle, but only if we're talking about a unit sphere, a sphere with a radius of 1.
Okay, so the bigger the triangle, the larger its spherical excess, and therefore the larger its area.
You got it. It's all because of that curvature again. It's like the triangle's trying to stretch out, but the sphere keeps it curved, and that creates the excess.
So even though the spherical excess might seem small, it has a big impact on how we measure and understand things on a sphere. It makes you realize that even tiny differences can matter a lot when you're dealing with large scales.
You said it. It's all about perspective, right? And speaking of perspective, in our final segment, we're going to take a step back and explore some of the surprising connections between spherical trigonometry and other areas of math.
Ooh, I'm ready for some mind-blowing connections. Bring it on. We've covered a lot of ground in this deep dive into spherical trigonometry. We started with the basics, looked at real-world applications, and now I'm excited to explore some of those hidden connections you mentioned, the links between spherical trigonometry and other areas of math.
It's really fascinating stuff. We've already seen how it builds on plane trigonometry, but it doesn't stop there. There are connections to calculus, linear algebra, even vector analysis. It's like spherical trigonometry is this bridge between different mathematical worlds.
Okay, I'm intrigued. Let's start with calculus. I remember you mentioning something called solid angle and how it relates to spherical excess. Can you refresh my memory on that?
Sure. Imagine a point and it's surrounded by a closed surface, like a sphere or some other shape. The solid angle at that point basically measures how much of the surrounding space is enclosed by that surface.
So instead of a regular angle on a flat surface, we're talking about a three-dimensional angle.
Exactly. It's like a measure of how much that point sees of the surrounding space. And instead of degrees, we measure solid angles in steradians.
Okay, I think I'm starting to picture it. But how does this connect to spherical excess?
Well, the cool thing is that the spherical excess of a triangle on a unit sphere is equal to the solid angle that triangle makes at the center of the sphere. It's like the spherical excess is telling us how much of that three-dimensional space the triangle takes up.
Wow, that's a neat connection. So how does this relate to calculus specifically?
Solid angles pop up all over the place in calculus, especially in physics and engineering, like when you're dealing with fluxes, which is basically how much of something is flowing through a surface, or when you're working with fields, like gravitational fields or electric fields.
So those calculations need to take into account those three-dimensional angles.
Exactly, and that's where the concept of solid angle comes in handy.
Okay, now let's jump to linear algebra. I'm
Hmm.
curious about this connection because it seems like a big leap from triangles and spheres to matrices.
Right. How do those two worlds even relate? Well, you know how matrices are used to represent transformations, like rotations.
Yeah, I remember that from linear algebra.
Right. So, turns out you can actually represent rotations in three-dimensional space using matrices. And guess what? A lot of those spherical trigonometry formulas can be understood and even derived using these rotation matrices.
Whoa, so we can express the relationships between spherical triangles using matrices.
Exactly. It's a more abstract way of looking at it, but it's pretty powerful. And it lets us use the tools of linear algebra to analyze those relationships, which can be super helpful.
So it's like another perspective on the same problem.
Exactly. Different tools for different jobs, right? Okay, now for our last connection vector analysis.
Okay, I'm ready. How do vectors fit into all of this?
Well, in vector analysis, we have those handy tools like dot products and cross products, right? And it turns out you can use those to prove a lot of those spherical trigonometry identities.
So it's another way of understanding those relationships between sides and angles.
You got it. It just shows how interconnected math really is.
I love that. It's like spherical trigonometry is this central hub that connects to all these different branches of math.
Right. It's like a secret passageway between different mathematical worlds.
This whole deep dive has been amazing. We've gone from basic triangles on a sphere to real-world applications to connections with calculus, linear algebra, and vectors. It's mind-blowing how much depth there is to this topic.
It's been a blast exploring it with you. Spherical trigonometry is such a rich and fascinating field.
It really is. I am definitely leaving with a newfound appreciation for it. And to all our listeners out there, we hope you've enjoyed this journey into spherical trigonometry as much as we have. Keep those minds curious and keep exploring the amazing world of math.